Hello friends, welcome back to this channel. However, if you are new, don't forget to subscribe. Today we are going to look at what a mole is. If you're a biologist, you may think of it as a small mammal that has small eyes and ears with front limbs that are modified for digging. However, to the chemists, it will not mean this small mammal. A mole is basically a chemist's measure of the amount of a given substance. So when you look at a mole, just like you have heard of a pair, meaning two things, when you have a pair of shoes or a pair of penguins, it means two things. So even a mole will have a certain number attached to it, just like you may hear a dozen, meaning 12 things, or a dozen of eggs, that means you have 12 eggs, or a dozen of donuts. So a mole will basically be a measure of a substance. Let's find out the magic number for a mole. A mole has 602 hexillion things in it. We shall have 21 zeros after 602. 3, 6, 9, 12, 15, 18, 21. 602 hexillion things make up a mole. So if you have a dozen donuts, that means you have 12 donuts. But if you have a mole of donuts, that means you'll have 602 hexillion donuts. 602 hexillion is a very large number, to the extent that if you are carrying out a mathematical expression and you want to multiply it by a certain number, you may find yourself going back to count the number of zeros to ensure that they are 21, if not needing a very large piece of paper to calculate that given number. So Avogadro came up with this number, and it's now called the Avogadro's number, but because the number is very lengthy, it could be quite tiresome, so we have to somehow shorten it using the scientific notation, and it will become 6.02 times 10 to power 23. So this is the scientific notation that's normally used to represent this Avogadro's number. One mole of a chemical species contains the same number of particles as there are atoms in 12 grams of the isotope carbon-12. We know carbon has different types of isotopes, carbon-13, carbon-14, but in this case emphasis is on carbon-12. So one mole of a chemical species, be it an element or a compound, will contain the same number of elements or compounds as there are atoms in 12 grams of carbon-12. This means that if you get your weighing scale and you place 12 grams here, the normal 12 grams that we deal with in everyday life, and then you place your other carbon 12 onto this other side until it levels off or balances, we shall realize that the number of carbon atoms of carbon-12 placed on this other part will always be equal to 602 hexillion atoms. So the number of carbon atoms that will always balance 12 grams will be 602 hexillion atoms, which are given by this Avogadro's number. Avogadro's number is the magic number for one mole. So this implies that one mole of hydrogen is equal to 6.02 times 10 to power 23 molecules of hydrogen. However, if we have 1 mole of hydrogen, this will mean that we have 6.02 times 10 to power 23 times 2 atoms. Why? Because in one molecule of hydrogen, the diatomic molecule, we have 2 atoms of hydrogen. That's why we have to multiply it by 2. What about 1 mole of water? How many atoms will be present? Feel free to pause the video and give it a try. How many atoms will be present in 1 mole of water? Okay, so 1 mole of water will have 6.02 times 10 to power 23 times 3 atoms present, because water will contain 2 atoms of hydrogen plus 1 atom of oxygen, which will make 3 atoms. So we normally confuse the word mole with the word molecule. However, mole is not an abbreviation of molecule. Mole is just a chemist's measure of the amount of a given substance. So the question is, why use 12 grams basically of carbon? Because we have seen that 12 grams of carbon, 12, will contain 602 hexillion atoms of carbon. So one thing to notice that 12 is basically the atomic mass of carbon 12 isotope. 6 protons and 6 neutrons, the sum becoming 12. And as such, this means that the atomic mass stroke atomic weight of carbon is equal to exactly 1 mole of carbon. So the 12, which is the sum of protons and neutrons, becomes equal to the 12 grams, the real weight that we measure in real life, will be equal to 1 mole of carbon. That's why we prefer to use 12 grams, because it's equal to the sum of protons and neutrons. However, we have seen that these 12 grams will contain 602 hexillion atoms of carbon. But for simplicity, they now become equal to the 12 grams, which will be still 1 mole of carbon. The atomic mass of carbon 12 is 12, and the mass of 1 mole of carbon is 12 grams. Using the same knowledge of carbon as a reference, the atomic weights you see in the periodic table are also equal to 1 mole of those substances. For example, when you look at sodium, usually elements in the periodic table are represented like this, with the number at the top representing the atomic number, while the number below, the symbol for that element, will represent the atomic mass. So sodium being 22.988, the atomic weight of 1 mole of sodium will be relatively equal to 23. While for lithium, the atomic number for lithium is 3. However, 1 mole of lithium will weigh 6.941. So just like carbon, we can always tell the atomic weights for 1 mole from the periodic table. So lithium, it will be 6.941. This is why we state atomic and molecular masses in units of grams per mole, or G per mole. So if you have 23 grams of sodium, we can say 23 grams per mole. Or if you have 6.9 grams of lithium, we can say 6.9 grams per mole, because that will be 1 mole of lithium. However, for molecular masses, for example, water, our water, we had seen that it has 3 atoms. We shall add the mass for hydrogen, 2 of them, the mass for oxygen, and the sum will be 18. So we can say that the molecular mass for water will be 18 grams per mole, because 1 mole of water will now be weighing the sum of the 3 atoms. What can we do with the moles? We can use the unit to make calculations based on balanced chemical equations. For example, copper reacting with oxygen to form copper 2 oxide. This is a balanced chemical equation. With this equation, we are able to predict the amount of the product made, which is copper 2 oxide, or the amount of the reactants needed, be it copper or oxygen. Provided we have the number of moles of each reacting species, we can be able to use the mole ratios to predict the amount of a given product that we shall have at the end of the reaction, or the amount of the given reactants we shall need to produce a given amount of the product. So that's how we can use moles in our everyday lives. How big is a mole? Or how large is Avogadro's number? Assuming you fill your house with a heap of jelly beans, that heap could be quite big. However, if you fill a stadium, football stadium, with jelly beans, that heap could be far bigger than that of your house, probably. But imagine if you could have a mole of jelly beans, 602 hexillion jelly beans. This could be as big as planet Earth. You could be able to fill the whole planet Earth with jelly beans. That's how big Avogadro's number is, if at all the size of the particles, molecules, or atoms we are looking at are equal to that of each individual size of this jelly bean. Let's take a look at a different aspect, we have our donuts, a mole of donuts. We shall be having 602 hexillion donuts. So if you pile one donut on top of the other, you will be able to reach from Earth, or to travel from Earth to the Sun and back 200 billion times. That's a very big number, 200 billion times from the Earth to the Sun and back. That's how big a mole could be if at all you have the size of donuts placed on top of one another. However, in chemistry, we are not talking about donuts or jelly beans. We are talking about atoms. Let's have a look at a mole of sulfur atoms. So sulfur is normally a yellow powder. So this is our sulfur. So if you get 32 grams, of sulfur on a weighing scale, you will be having 1 mole of sulfur. So here we have 1 mole of sulfur, and we shall be having 602 sulfur atoms in this dish here. So here we have 602 hexillion sulfur atoms. Just like 602 hexillion jelly beans could fill the whole planet Earth, here 602 hexillion sulfur atoms will be just in this dish. So this shows you how small atoms are. And 1 mole will somehow simplify calculations because we are dealing with a very large figure, just that in terms of atoms, this number or the size of this figure seems small. So 1 mole of sulfur atoms will be present in this dish. So here we have 1 mole of sulfur because it is weighing 32. Obviously, the weight of the dish is scattered 4, and the mass that we are seeing here is the mass of 1 mole of sulfur. So in this case, we shall have 6.02 times 10 to the power 23 sulfur atoms here. So that's how we are able to tell 1 mole of a given substance. Even for carbon, you will just have to weigh the mass of carbon. Once you have 12 grams of carbon placed in this dish, then you will be having 1 mole of carbon. I have a question for you. Why do you think carbon is used as the reference? We are talking about carbon-12 isotope. We are talking about Avogadro's number coming from the number of carbon atoms present in 12 grams of carbon-12. Why don't we use hydrogen? Or why don't we use oxygen? Please let me know in the comment section. Or if you have any idea or a view or a question, please leave it in the comment section. I'll try my best to get back to you. Don't forget to like, subscribe, and hit that bell notification so that you don't miss any of our related content whenever we upload it. Stay safe.